So today and tomorrow also we will continue in the online mode. Then remaining classes will be in offline mode. I don't think we are left with too many classes now. Okay, let us begin. So we have been discussing water jet machining in the previous class. So there we have seen the basic principle of water jet machining and the components of water jet machining setup, and we have been discussing those components one by one. So now let us start and revise those things quickly, and we will continue with the same topic, and we will see what are the other aspects of water jet machining. Few small derivations or formula we will see, few numericals will follow. So just I'm coming from the beginning. Very quickly we will go through these slides. Water jet machining. Okay, it is very much similar to abrasive jet machining. So in both the cases we have a jet. Okay, that jet is coming and hitting the workpiece, and the workpiece material is removed. But the difference here is, here we are using water as the cutting medium. In the abrasive jet machining, what was the medium? How the cutting is happening there?
Abrasive particles.
Yeah. So abrasive particles and carried by the gas. So that is a mixture of abrasives and gas that is coming like a jet and hitting the workpiece, and brittle fracture of the workpiece is taking place if the workpiece is brittle in nature. So in that way we are removing the material. So mostly abrasive jet machining is very much suitable for the machining of brittle materials only. But however, it can be used for ductile materials with less effectiveness or efficiency. Now coming to the water jet, now we are using water jet. The water in the form of jet. So this jet will have high pressure and it will be coming at high velocity and hitting the workpiece, and it is now eroding the material. Okay, erosion due to water, water jet impingement on the workpiece. Here water jet machining is mostly suitable for soft materials, okay, not for very hard material or high strength material. Because you can imagine water jet cutting the material. So for that we need high intensity water jet. So even with that also we cannot cut very hard materials, high strength materials. So these are some of the examples of water jet machining. So these rocks, okay, they have taken the given shapes due to the erosion caused by the water. Okay, you can see all the figures. Over a period, these tides, okay, water tides are hitting the rock, and they are they have eroded a very minor amount of material. So again, water tide will hit and minor amount of material will be eroded. Like that over a period. Over a period means in some years, 100 years duration like that. So these kind of caves were naturally formed. So mechanism. So mainly you'll have a nozzle, and you'll have workpiece that is shown in green color there, and SOD, stand-off distance. So water jet is coming and hitting the workpiece. So you can see the range of velocity and pressure. So pressure is in the order of some 8,000 bar, and velocity is about some 400 meter per second. So both are very, very high. Okay, 1400 meter per second is very fast, and P max pressure 8,000 bar is very, very high. If you talk about 10 bar, that is also good amount of pressure. Now we are talking about 8,000 bar. Okay, high intensity is there. Now the condition for the material removal to take place in water jet machining is that pressure, stagnation pressure should be equal to the, stagnation pressure will be converted to velocity, but whatever pressure you are using, that must be more than the flow stress of the workpiece material. Okay, if it exceeds only, cutting will take place. Is it clear?
Yes, sir.
Now this equipment also we have seen, we'll just show it once again. So these are the elements of the water jet machining setup. So first is there is one oil tank or reservoir. So here this oil tank is to run the pump. Okay. Apart from water, you can use other jets. That is another issue. But here, as far as this figure is concerned, the oil tank shown here, okay, that is used to run the pump. So to run the pump, you can use the oil, or directly electric pump can also be used. That is another thing. Okay. Now pump is running, and now there is one intensifier. Okay. So you are pumping the water into the intensifier at low pressure. Now intensifier is increasing the pressure by compressing the water. Now that compressed water now is going into the accumulator. Duty of the accumulator is to maintain the water at that same pressure. Okay, it is acting as the reservoir of water at high pressure. Now that pressure will be coming down. Okay, so this is accumulator. So highly pressurized water now is entering into this tube, and of course it will pass through the valve. So by using this valve, you can control how much amount of water, okay, water flow rate can be controlled. Now it will enter the nozzle finally. Okay, through nozzle, you are reducing the diameter. You can see the nozzle, it may have, okay, a flat hole like this, cylindrical hole, or it may have a tapered hole itself. If there is a tapered hole, again the pressure is increasing inside the nozzle. Now the water is coming like a jet and hitting the given workpiece. Okay, we are maintaining one SOD. Now there is a catcher just below the workpiece. Now the purpose of the catcher is to catch the water and the debris formed during the cutting process. Why we are using a specific catcher is because this water jet is coming at high velocity and high pressure. Even after hitting this also, it will be left with some good amount of velocity. Okay, 1400 meter per second, if that is the velocity. After cutting the workpiece also, maybe some 300 meter per second velocity may be left for the jet. So if the water is coming and hitting any other material with that velocity, again erosion will take place. To avoid that, we are carefully catching that water in a tank. Okay. So these are the equipments related to water jet machining: hydraulic pump, intensifier, accumulator, catcher, high pressure tubing. Okay. So
Hello,
this
sir.
is one trip. Yeah. Anybody speaking?
Yes, sir.
Yeah. Tell me.
Sir, if we are using only high velocity water jet, like if we consider water as a grid, so the grid.
Water,
So water is a grid, sir.
water as a grid.
Grid, sir. Grid. GRIT. Grid, sir.
Grid.
Yes. So the grid density will be less than what we use in abrasive jet machining, sir.
Yes, definitely.
So the cutting will not be, sir, that much means.
Yeah, here if you compare abrasive jet machining and water jet machining, there are many limitations in water jet machining. Okay. You cannot cut high strength or brittle materials. That is what I have stated very clearly. you will generally cut soft materials, okay, which have less strength. Okay, those types of materials only will cut using water jet. But we have certain advantages in water jet compared to abrasive jet. In abrasive jet, we are generating, we are polluting the environment a lot. Gas and abrasive mixture hitting the workpiece at high velocity. So a lot of dust is coming out. Okay, we are polluting the environment. So here there is no pollution. Zero pollution, you can say. Environmental friendly. And okay, whatever workpiece that is cut here, so there will not be any other surface integrity problem for the workpiece. Okay, workpiece is not getting heated up. Even abrasive jet machining also heat is less. Okay, very, very less, almost negligible. So we will use water jet machining wherever applicable. That's it. We cannot cut any material using water jet. That is not possible. But wherever we can cut the soft materials, we can use it. Okay. So that is the purpose. Is it clear?
Yes, sir. Thank you, sir.
Okay. So this is one typical water jet machining setup. You can see. So this is a CNC control. Okay. So you can use the CNC programming and control the path followed by the water jet so that you can cut any desired shape. So hydraulic pump, whatever equipment we have seen, these are the functions. You can use one electric motor. Power is in the range of 30 kilowatt. Okay, very high power. So it supplies oils at pressure 120 bar. We have seen these slides in the previous class. Just I'm going a little bit quick. Now, compressed oil drives a reciprocating plunger pump termed as intensifier. That oil reservoir, whatever is there, that is used to run the intensifier. Intensifier is one kind of pump only, cylinder. Okay, reciprocating pump. Okay. So there are two aspects here. One pump is taking the water and supplying to intensifier. Now another is intensifier itself. Intensifier is run by the oil that is supplied. So hydraulic pump offers complete flexibility for cutting and cleaning applications. So these things we have seen. If you have any particular doubt, you can ask me. Otherwise, we'll skip this. So next is intensifier. So coming to intensifier, its purpose is to increase the pressure. Okay. So this is a device used to increase the intensity of pressure of water from a large amount of water at low pressure using the hydraulic energy available, that is hydraulic intensifier. If you see for this cylindrical part, okay, you consider this cross section area. Okay. So, and if you take this is a tube, you take this cross section area. Now you are just using this plunger or piston and whatever water is there here, okay, you will just compress it and force it to pass through this pipe. Okay, diameter is greatly reduced, so pressure will increase. Understand? Same thing can be seen here. pH into A large. A large means this one. Okay, cross section area of that. PW is working pressure. Okay, A small. So A small is this. So that must be equal. Okay, as for the last way that we know in fluid mechanics. So this is equal. Now PW can be expressed as pH into A large by A small. Now what is this A large by A small can be written as A ratio. Okay, ratio of the cross sections. Working pressure is equal to P is you can say hydraulic pressure, okay, into A ratio. Is it clear?
Yes, sir.
So A ratio is cross section of two cylinders. So you are using this is one cylinder. Okay, this is one small cylinder or a pipe. Okay. Now, if the hydraulic pressure is set to 100 bar, that means pH is 100 bar, and the area ratio is 40. This ratio is 40. Then PW is equal to 4000 bar. Just application of this formula. Now accumulator, okay, it maintains the continuous flow of the high pressure water and eliminates pressure fluctuations. Okay, so through intensifier, you are increasing the pressure. So 40 bar to some 400 bar, let us say, for example. Now this intensifier is continuously working and increasing the pressure. Okay, definitely during the functioning of the intensifier, there can be some fluctuations. Okay, because of change in the power supply. Okay, like that. So it will not be always exactly 400 bar. It may be sometimes 350 bar only, sometimes 420 bar, etc. Okay, based on the movement of the intensifier. So whatever intensified water is there, that is now going into the accumulator. Whatever water is available in the accumulator, all the water will have some okay, same kind of pressure inside the intensifier after going into it. Okay. Now there will be uniformity, okay, in the pressure that is supplied to the valve from the intensifier or the accumulator. Have you got this point? It is acting as a stabilizer. Accumulator is acting as a stabilizer for the water, high pressure water. So you will get the uniform pressure from the accumulator, not from the intensifier. Okay. And you can see second point, it relies on the compressibility of the water. Okay. You know what is compressibility? You might have studied in fluid mechanics. So water should be reduced in volume. Okay. If something can be reduced in its volume, then we can say it has some compressibility in order to maintain uniform discharge pressure in water jet. This is okay. So it acts like a flywheel of an engine. The function of flywheel in an engine is to store the energy. Okay, you are using the cylinder. Cylinder is moving the crank. Okay, so now you are attaching a flywheel onto that shaft so that the energy is stored on the flywheel. So you can now get the uniform velocity or the stored energy from the flywheel. So same function, similar function is delivered by the accumulator here. High pressure tubing is required because those tubes should also be able to withstand about 400 megapascal pressure. Typically diameters are 6 to 14 mm. So this is one thing. Tubing allows for flexible movement of the cutting head. Okay. So cutting head, okay, that whatever nozzle is attached, so that has to move freely in different directions. So if you use okay, flexible tubes, then only it is possible. So water will flow through those pipes. Now coming to nozzle, you can use synthetic sapphire. So diameter orifice is 0.2 to 0.4 mm. So similar to the diameter that we have used in abrasive jet machining. So we are getting okay, coherent water jet by using that nozzle. So we are getting a life of 200 hours for the nozzle. Okay. Okay. So here, okay, water jet cutting head promotes compact design of water jet cutting head promotes integration with motion control systems ranging from 2-axis to multi-axis tables. So what is the meaning? Okay, if you have compact design, very small, okay, very good design for the head that is moving in the water jet. Head contains the nozzle. Okay, so that can be attached to CNC machines. So you can control the motion of that head using CNC program, and you can cut complex shapes. Velocity of the water jet thus formed can be estimated assuming no losses. So head design is very, very important. So if it is properly done, there will not be any losses in the pressure or the velocity. Now VW, working velocity, okay, or water velocity that is coming out from the nozzle is equal to this square root of 2 PW by rho W. PW is water pressure, rho W is water intensity. So pressure and velocity, okay, you are using Bernoulli's equation, pressure energy plus kinetic energy, okay, is equal to a constant. Okay, based on that you can get, are equal to total energy 0. Here the point is pressure energy, okay, entire pressure energy is converted to kinetic energy. That is the concept. Okay. Is it clear? Any doubt here? Half mv square is equal to this mv square. No? You can take this pressure energy. What is it clear? Then half rho v square. What is m? Volume. Volume into density. Volume, let us say I am keeping it here. So it is equal to pressure. Okay. Now here you have to take pressure into volume. Pressure energy is pressure into volume. So volume cancelled out. So V is equal to square root of 2 PW by rho W. Some extra lines are coming. You have to bear with that. Is it clear? Any doubt here in this slide?
No doubt, sir.
Clear, sir.
So that is VW. Now the function of catcher. It acts as a reservoir for collecting the machining debris. Okay, you have seen that in figure. Now catcher is used to absorb the residual energy of the jet and dissipate the same. That is one more thing. There are two functions here. One is to collect the debris that are formed during the water jet machining. Second is absorb the residual energy. So this water jet has some energy left in it, okay, even after cutting. So that will be, okay, now nullified, okay, once the water is entering the catcher. Now reduces the noise levels associated with the reduction in the velocity of the water jet from Mach 3 to subsonic levels. So water velocity will be around some, what is Mach 3 velocity? 3 times the velocity of the sound. Okay, so about 330 is the velocity of the sound. So about 1000 meter per second to subsonic levels below 330. Understand? So water jet velocity will be reduced in the catcher. Okay, there is a pool of water and the water jet and coming and hitting this pool at some 1000 meter per second, let us say. And it will be now reduced to some 100 meter per second upon hitting Okay, the velocity is reduced. Now there are different types of catchers here. One is a tube type, submerged steel balls, and titanium diboride. Okay, plate. Okay, that can also be used for as the catcher. Now you can see if it is simple water, jet is coming here and diverging in the water and it is losing its pressure. And sometimes to reduce the water velocity, you are using some steel balls here. Okay, tungsten carbide, ceramic balls can also be used to reduce the water jet pressure. And you are using one plate also here, just below your workpiece, you are putting a plate here. Okay, titanium bicarbonate, which is brittle. Okay, it will break. Okay, just very easily. So, and water will lose its velocity. Otherwise, you can directly use a plate here. Okay, but it will affect your cutting process. Now, what you can see is you can arrange them in this fashion, like this. Okay, using some equipment or stands. So, water jet is coming here, it is hitting here, it is losing some pressure. It will come here again, it will hit, it will lose some pressure. Like that, step by step, it will lose the pressure. Not pressure, velocity. Okay, is it clear?
Yes,
Yes,
sir.
sir.
Now material removal rate. So velocity is given by CV square root of 2p by rho. Now what are these? P is the water pressure, rho is water density, CV is a velocity coefficient of the orifice. Okay. So we have seen V is equal to square root of 2p by rho. Earlier we have seen that then pressure energy is converted to kinetic energy. Now this extra coefficient CV is coming because some velocity is lost within the orifice itself. The volume flow rate of water can be expressed as Q. What is that? Q Cc into V into A. Volume flow rate. So V is velocity, A is cross sectional area. So volume by time. V into A is volume by time only. So volume flow rate is has come. Cc is the coefficient of vena contracta. Okay. So this is a reduction in the cross section of the nozzle. Okay, that ratio is given by Cc. Now you can see Q can be written as Cc into V into pi d square by 4 is the cross sectional area. Okay. Q can be further written as Cc into V. For V, we are using this formula now. Cv, this one, and pi d square by 4. Now, what is Q? Volume flow rate. Now, Q can be further expressed as Cd into pi d square by 4. Now, what is a Cd? This multiplication. Cc into Cv. Okay. So, total power of the water jet is P into Q. Power. So, pressure into volume flow rate is giving the power. Is it clear? Pressure into volume flow rate. Volume flow rate means mm cube per, suppose mm cube per second, for example, unit. Okay, it may be meters, meter cube per second, hour, whatever. Now pressure is Newton per mm square. So you can cancel out this. So Newton mm per second is power only. Okay, or Newton meter per second is watt. So P into Q. So you multiply those two. Okay, so if you take P here, or if the P is going inside this square, it will become P cube. So in water jet machining, MRR is proportional to power. So this is obvious. Okay, through the experimental evidence, you can find that MRR is proportional to the power that is being used. So you can equate MRR is equal to K times of power. Okay, so MRR can be expressed as this: K times of CD pi d square by 4 square root of 2p cube by rho. Now K is a constant. It depends on specific energy of the work material. So how do you find the K? Okay, it depends on the workpiece material. Okay, so for a given workpiece, K is given, which was found experimentally and okay, standardized. So finally, this is the expression for material removal rate in water jet machining. Is it clear?
Yes, sir.
Yes, sir.
Now, once MRR is covered, now the next step is surface finish. So surface finish in water jet machining depends mainly on 5 factors: design of nozzle, jet velocity, cutting speed, depth of cut, properties like hardness. Okay, these properties will affect the surface finish. So design of nozzle, what does it mean? Nozzle can be, it may have, this cross section may be different. It can be circular or rectangular. That is one thing. And okay, rectangular type nozzle we have seen earlier in abrasive jet machining. Okay, straight nozzle. Based on that, the surface finish will vary. Jet velocity, obviously, at how much velocity the jet is coming. So that will also impact the our surface finish. Cutting speed, at how much speed the jet is moving during cutting process. Now depth of cut, how much how much depth the material is being cut. So some of the properties of the workpiece, for example, hardness. Okay, if the workpiece is hard, surface finish may not be good, because it is now due to brittle fracture, the material will be removed. So in that case, surface finish will not be good. Cutting speed also, cutting speed should be maintained at optimum level. It should not be too slow or too fast. If it is too fast, material will not be properly cut, surface finish will be poor. Okay, and if it is too slow also, okay, lot of debris will be entrapped in that gap only. Okay, it has to move at optimum speed. Particularly, it should not go at high speed. So then you will not get proper cut. So jet velocity is important. Higher the velocity, better will be the cut. Geometry and surface finish. Hardness of nozzle material. Okay, in water jet machining, wear rate of nozzle. So here we are talking about wear rate of nozzle. This is also important, because nozzle has limited life only, some 200 hours. So how to maximize the life of the nozzle? That is also one important criteria. So this, in water jet machining, wear rate of nozzle depends on hardness of nozzle material. So preferably we should have very good hardness for the nozzle material. Remember, hardness and brittleness are different. Okay. So if it is brittle, it will break easily. If it is hard, okay, it will not deform easily. Now pressure of the jet. If the pressure of the jet is high, nozzle wear rate will be high. But anyhow, we should have high pressure, okay, for cutting purpose in water jet machining. Now, how much? So based on the requirement, you have to decide how much pressure is required for the given cut. Okay, use that much amount of pressure. Don't go beyond. Okay, don't use excessive pressure. If you are using extra pressure, it is waste of energy. Okay, waste of power. Not only that, your nozzle will also lose its life quickly. Now, velocity of the jet. At what velocity the jet is coming out. Okay, if the velocity is high, nozzle wear rate is high. Nozzle design again. So based on the shape, if it is circular, wear rate may be less. If the nozzle cross section, okay, jet is coming out from the nozzle, if that cross section is having some square type, wear will be more if you have those sharp corners like that. Now process parameters in case of water jet machining.
Sir, excuse me, sir.
Hmm.
Sir, there can be another factor also, na, sir, like in how much continuous way the means without any jerks and movement of the water, like suddenly it is coming, then stopping, then coming, like fatigue type of wear.
Then also wear rate will be more. Okay, if it is not uniformly coming out. Okay, that is okay, agreed. But generally, what we are assuming is, we assume that machine is perfect. There is no problem in the water flow, etc. Okay, if that is the case, what are the factors in our control? Okay, if jerks are there, of course we have to control that. Okay, that is generally, that is one disturbance during machining process. If water is not coming uniformly, okay, through the pipe, you have to stop the machine, you have to rectify it, and you have to make sure that water is coming at uniform velocity or uniformly. Okay. Then you will run the machine. But yes, if it is not coming uniformly, if there are some jerks, again wear will be high. Okay, that is not the major issue. Okay, generally, if there is such kind of issue, you have to okay, troubleshoot that. Then only will run the machine. Okay.
Yes, sir.
Okay. Now process parameters. So potential energy of water jet is converted into kinetic energy. Okay, this is what is happening. We have, this is the main principle also. Pressure is converted to velocity. Now this range is about 4000 bar and velocity is about 1000 meter per second. Okay. So these are a few typical values only. Okay, earlier we have seen 1400 bar pressure and we have seen 800 meter per second like that. Okay. Now standoff distance is about 2.5 to 6 mm. Typical range is that. Now nozzle diameter is about 0.1 to 0.3. Earlier we have talked about 0.2 to 0.4. Okay, all these are correct only in that range. So however, for materials used in PCBs, printed circuit boards, it may be increased to 13 to 19 mm. Okay. What is that? This one. You can increase the nozzle diameter. If you want only less velocity, okay. So you can increase the nozzle diameter, or you can increase the distance, standoff distance. Now tolerances are in the range of plus or minus 25 micron on thin material. So after cutting, so if you see the tolerance, now your okay, your requirement is to cut 2 mm, okay, width slot, 2 mm width. Okay, that kind of slot you wanted to cut. Now, tolerance range is about plus or minus 25 micron in case of water jet machining. Surface finish, if you see, it is about 125 to 250 micrometer. So these are the typical ranges for various process parameters. Coming to jet fluid, so it must possess low viscosity. What is the jet fluid? If you are talking about water jet machining, we are talking about water. Okay, you can use other fluids also. So must possess low viscosity to minimize the energy losses. If viscosity is high, okay, it will not come out from the nozzle quickly. So you will lose a lot of energy. So preferably low viscosity, non-corrosive, because that water or fluid is in contact with many components, tubes, okay, intensifier, pump, etc. So it should be non-corrosive, non-toxic also. So you should not get uh, any hazardous fumes or okay, gases from that. Preferably inexpensive. Okay, it should be cheaply available. So most of these are satisfied by water. Now typical pressures used are again some 1000 MPa, and you will generate a power. Depending upon the requirement, it can be around 8 kilowatt power. Sorry, 80 kilowatt power. So that range is there. Based on application, we have to use. Now water is commonly used for cutting alloy steels. So mainly water is used because it has a low viscosity. Okay, mainly it is inexpensive, non-toxic. But corrosion problem is there with water when you are using some ferrous materials in your equipment. Now you see, alcohol is used for cutting meat. Water jet machining is used for cutting the vegetables, meat, etc. in some restaurants. Okay, if you want some good designs, okay, for appearance purpose. So some decorative items will be there on food. So they will be cut. So generally in normal hotels, they will cut with restaurants, they will cut with some knife, etc. So here using CNC water jet machines also, you will cut these food in different shapes. Okay. So alcohol can be used for cutting meat. Cooking oils are recommended for cutting frozen foods. So they can be part of your main dish. Okay. Now jet velocities range between 540 to 1400 meter per second. We have seen this again and again. Now workpiece. Coming to the workpiece, so brittle materials will fracture while ductile ones will cut well. So water jet machining is more suitable for ductile materials. Okay. Brittle materials also it can cut, but accuracy will be less because of breakage of that workpiece material. Material thickness ranges from 0.8 to 25 mm or more, depending upon the material properties. If you are cutting soft material, depth can be high. If the material is very hard, then you can cut only thin foils. So based on the material, you can see now the thickness. If you are cutting leather, okay, you can cut around 2.2 thickness. Okay, and your feed rate means moving velocity of the jet. You can use 20 meter per minute. Okay, you can cut like this. So vinyl chloride, polyester, these are some kind of plastics, Kevlar. So you can use these kind of thicknesses, 2 to 3. So these are the feed rates. Feed rate for vinyl chloride is very less. Slowly you have to cut. Polyester very high. Kevlar, okay, 3. If you are cutting graphite, thickness 2.3, feed rate 5. Gypsum board. Okay, gypsum, you know, that is widely used outside. So you can cut up to 10. Its strength is less. So feed rate is 6. Corrugated boards, okay. If you are cutting boards, then 7 to 200. 7 is the thickness, feed rate is 200. If you are cutting some plywood, 6 and 1. You see, if you observe all these materials, so these are low strength materials, okay, soft materials in most of the cases. So for cutting these materials, these are the recommended ranges. Now, causes for process response in water jet. So this is again a fishbone diagram. So what are the responses? What are the points that are interested in water jet machining? Machining rate or material removal rate. Okay. How fast I can cut the material. How accurately I will cut the material. Okay. Accuracy, that means geometric accuracy and dimensional accuracy. Both are similar only. Okay, there is not much difference here. So geometric accuracy means you are talking about the shape. Okay, how accurately you can cut the shape. Dimensional means, okay, how tightly you are cutting, how close the tolerances are. That is the meaning here. Now surface roughness is one important aspect you will look at. So mainly material removal rate, surface roughness, accuracy. These are our main points, okay, that we are interested in. So that depends on jet fluid, nozzle, process parameters, workpiece parameters. Now, if you subdivide those, jet fluid, what is the type? That means what is the jet fluid, whether it is water or any other liquid. What is the velocity of the jet? What is the pressure? What is the flow rate? What is the viscosity? So these are the parameters related to jet, water jet, or the fluid. Okay, we are talking about the fluid. Now coming to the nozzle, what is the diameter of the nozzle? What is the cross section shape? What is the type of the nozzle? Whether you are using sapphire, tungsten carbide, etc. Okay. Now coming to the process parameters, standoff distance. What is the distance? Okay. What is the pressure at which the jet is just coming from the nozzle tip? What is the velocity at which the nozzle is moving? Related to workpiece, what is the hardness of the workpiece material? What is the thickness of the workpiece material you are cutting? What is the material itself? Okay. So all these factors will influence this material removal rate, accuracy, and surface finish. Okay, let us continue. Is it clear up to this point? Any doubt here?
Yes, sir. All please.
Okay. It is not any, okay. These unconventional machining processes are not difficult to understand, particularly this water jet machining, abrasive jet machining, etc. We can go a little bit quickly. Advantages. So water is cheap. This is one major advantage. Non-toxic. Okay, that is also very clear. Easily or readily available and can be reused by filtering the debris. So in water jet machining, you have these advantages. Compared to abrasive jet machining, you can compare with abrasive jet machining. Okay, that is also unconventional machining. In abrasive jet machining, you have to purchase the abrasives which are costly. You are getting some dust, etc. Okay, that is dangerous. Okay, they are not cheaply available abrasives. And here, and that abrasive jet once used cannot be reused. Here you can filter and use because it is water. You can separate the debris from the water, solid particles from the water. In case of abrasive jet, both are solids only. Both are in okay, very micron level. Separating them is a difficult task. And anyhow, abrasives are losing their sharpness also. Now, true cold cutting process. So here no heat is generated. So there is no heat affected zone and mechanical stresses induced in the workpiece material. Now cuts can be started at any location without the need of pre-drilled holes. So you can keep the water jet at a particular location. So one hole will be drilled, then you can move the jet. Okay. So if you talk about any milling process, okay, if you want to cut any geometry suddenly from inside, you may have to drill a hole here first of all, then you put your cutter here, then move it. Okay, if the depth of cut is high. So that is not required here. There is no deflection to the rest of the workpiece. That means here water jet will be, there is no extra cutting that is taking place in case of water jet machining. Kerf width can be controlled very precisely. Why? Because the water jet, okay, is coming at high pressure and high velocity, and there is very less chance of flaring of this jet. Okay, it is coming out very straightly. Okay, so it is not deflecting due to environmental pressure, etc. Environmental pressure is at 1 bar. Now you are using 800 bar. So you see the difference. So environmental pressure will not affect the water jet movement here. So it has multi-directional cutting capacity. So you can move the jet, okay, the head that is containing the water jet in different directions. Okay. If you can control it using the CNC machines, you can move it in different directions and you can cut in those directions. Okay, we'll see some examples a little bit later. So this compared to ASIM, hazardous airborne dust contamination and waste disposal problems that are common when using other cleaning methods are eliminated. Water jet machine, abrasive jet machining, we know. So there is not much problem of disposing this waste. Okay, dust is not coming out. A simple fixturing eliminates costly and complicated tooling, which reduces turnaround time and lowers the cost. So here, fixtures. Okay, there no need to have complex fixtures for your workpiece material. You can simply hold with normal clamping system. Okay, compared to your conventional machining, if you are milling, okay, then you have to hold these workpiece very tightly because the cutting is taking place because of the mechanical force, okay, that is exerted by the tool on the workpiece. Here also pressure is converted to kinetic energy, but workpiece will not be moved due to lateral force is not there, only vertically force is acting. So fixture cost is less. Grinding and polishing are eliminated, reducing secondary operation cost. So finish will be so good. It will be in the range of 120 micron only. Okay. So further grinding particularly is not required. Narrow kerf. Narrow kerf because the water jet is in its shape. It is not losing its shape. Allows a tight nesting when multiple parts are cut from a single blank. Okay. You can cut multiple parts from a single blank easily. So you have taken a large blank, you have cut one shape here, other shape here, like that. Understand? It is ideal for roughing out material for near net shape. So you can, this also can be, you can use water jet machining for rough cut also. So you can roughly cut this, and after that you can go for the other finishing processes. Okay, so that can also be done. Okay, few more advantages are there. We'll complete the advantages, then we'll see disadvantages next class. So it is ideal for laser reflective materials such as copper and aluminum. Now what is this? Any idea here? So if you want to cut this aluminum or copper type material using laser jet machining, okay, it is difficult because laser will be reflected, it will not be absorbed. Okay, so in those cases, water jet machining is more suitable compared to that. Okay, laser cutting. There is a multiple head processing. This is also possible. Okay, so you can have multiple heads like this. Multiple water jets are there, so you can cut some 4 or 5 work pieces in a single go. That is also possible. So these are the advantages. So let us stop here and we'll discuss the remaining things in the next class. Next class we'll definitely complete this, and if possible we'll start another topic. Yeah, okay, I think you may have another class now. Do you have any class now? Somebody is speaking. Karthik, do you have any class now?
Yes, sir, DT.
Okay. Yeah, if you have any doubt, you can ask. Any doubt in this? Water jet machining? So it will be like a theory only. In all unconventional machining processes, you should be very clear about material removal mechanism or the principle. Okay, how the water jet is coming and hitting the workpiece, removing the material. That is the principle. Next is what are the components of that machining setup. For each component, you should know what is the material, what are the different aspects of that equipment. Then advantages, disadvantages, applications. And there can be few formulas for material removal rate calculation, power calculation, etc. So this is common for all the unconventional machining processes. Okay, you study in that manner. Okay, that's all for today. Thank you. We'll meet tomorrow. Have a
Thank
good
you,
day.
sir.
Thank you, sir.